Welcome to the 11th episode of our series, The Mother Earth. Amongst the terrestrial planets possessing solid crust, only the Earth supports a benevolent and breathable atmosphere for life to survive. But such an atmosphere did not surround it when its primeval low density crustal blocks surfaced above the protomantle material with higher density. That initial period of the Earth's history is referred to as the Hadean. Prior to the density differentiation process of crust formation, another consequential event took place in the Hadean. Subsequent to the core mantle separation, the lunar nebular mass was ejected from the upper portion of the Earth's protomantle. The proof for this speculation was furnished when, on accretion eventually, the Moon acquired a bulk density of 3.34 gram per cc, a low gravity, and no FeNi-rich core. Because of its low gravity, which is about 16% of the Earth's gravity, the Moon could not hold back or retain the gaseous emissions during the Hadean. That is, in its initial billion years volcanic history. The rarity of this initial atmosphere allowed free meteorite impacts, which left a highly cratered surface on this natural satellite of the Earth. Without any atmosphere interaction, the lunar surface remained unaffected by any erosion by wind and water. Therefore, the lunar characteristics and its crustal compositions have served as a reference surface for planetary comparisons and inferences. Radiometric ages of 4.2 to 4.5 billion years returned by the lunar samples approximately dated the event of ejection of the lunar nebular mass. This second event, Hadean event, accelerated the outgassing and cooling of the outer protomantle, fostering at the same time the upward migration of the Earth's still lighter crustal matter. In the first Hadean event, if you recall, the lighter silicate-dominated mantle, constituted of mainly the lithophile elements with minor chalcophile and siderophile elements, separated from the denser, mainly FeNi-rich metallic inner core and from the outer fluid core with chalcophile and siderophile elements. Following the ejection of lunar nebula, the primeval crustal blocks that floated up were constituted chiefly of such elements like sodium, potassium, calcium, barium, lithium, which readily combined with silicon, aluminum, and oxygen and formed the light density aluminosilicates, chiefly the large groups of potash feldspars and the plagioclase feldspars, which together formed almost 50% of the Earth's crust. The copious availability of the tetravalent silicon, trivalent aluminum, and bivalent oxygen was crucial at that stage of separation of the Earth's primeval crustal blocks. Besides the aluminosilicates, elements like Iron, magnesium, manganese, aluminum also combined with oxygen and with the wonder substance water H2O as the OH minus anion, constituting several minerals of the hydrated silicate groups like the amphibole group, mica group, and chloride group. The still available silicon and oxygen combined as polymorphs of the quartz group SiO2 and oxide minerals constituted of high valency elements like titanium, iron, chromium, phosphorus, sulfur, uranium, thorium, tin, and lead, among other minor elements which entered the compositions of silicates and oxides, were the lighter trivalent lanthanide group elements. Remember, lanthanum to samarium. These elements together are referred to as the oxyphile, oxygen-loving, or lithophile, rock-forming elements. The time that lapsed before the Earth achieved its compositionally distinguished layered structure of core, mantle, crust, in that order, was rather short on the astronomical scale, but long enough for elements to reposition themselves in the various mineral groups. It is estimated to have been accomplished in about 300 million years. It should have taken another 50 million years further for the Earth's surface to cool enough to initiate precipitation of the water vapor present in the Earth's atmosphere to eventually form the oceans and allow flowing water, the wonder substance, on its surface. Because of tectonic movements and speedy interaction with its atmosphere and water, only few small segments of that primeval crust are left on Earth. Efforts made to obtain radiometric ages on older and older rocks since the mid-20th century fathomed the time of crust formation. The radiometric measurements utilized the presence of isotopes of potassium and uranium present in feldspars and micas from the granitic rocks of the Earth's continental crust. Ascertained on geological grounds also, these data take the geological history backwards up to 3.8 to 4 billion years. It bolstered the speculation that blocks of the primordial crust surfaced around 4 billion years ago. It took almost 2 billion years further for the Earth's atmosphere to get sufficiently depleted in carbon dioxide and become oxygenated. Much later, stabilized the life on Earth. Only about 600 million years ago. In an earlier episode, we learnt that the Earth's nebula had compositional and thermal inputs caused by the entries of planetesimals and asteroids, didn't we? In its later history also, the Earth's crust has been impacted severely by meteorites and asteroids, triggering frequent volcanic activity. Volcanic eruptions on Earth have continued intermittently during its geological history. You know that the Earth is still volcanically active. There are frequent volcanic eruptions. The year 2020 was a period of more frequent volcanic eruptions on different parts of the Earth. Many eruptions have occurred along the arc-shaped chains of islands, some on the margins of its continental crust, while others have erupted on the ocean floors. Volcanoes have added light density melts laden with oxyphile and lithophile elements to its crust and volatiles to its atmosphere. The volatile matter is chiefly constituted of carbon dioxide, water vapor, ammonia, methane, and other elements which normally exist as gases, grouped as the atmophile elements. The lavas are generally at temperatures of 700 to 1200 degrees centigrade with low viscosity and originate from perennial source regions inside the Earth. These source regions are in fluid state and support actively moving convection current systems which brought about horizontal tectonic movements of the early formed crustal blocks also. Such fluid regions perhaps existed inside Mercury and Moon in their early history and are predicted inside Mars as revealed by the feeble but frequent seismicity recorded on its surface. Mercury and Moon ceased to be volcanically active in about 1 billion years, but volcanic activity accompanied by profuse outgassing of mainly carbon dioxide, about 96%, nitrogen, and trivial amounts of oxygen, water vapor, and other gases continues even at present on Venus. Its atmosphere is held back by the planet's gravity, but more importantly, because of its extremely slow spin. The overwhelming accumulation of these gases forces a dreadful greenhouse effect on its surface. Its surface temperature does not permit any condensation of its scanty water vapor. The Martian atmosphere is thin and rare, comprising of almost 95% carbon dioxide. The remaining 5% composition consists mainly of nitrogen, argon, and less than 1% oxygen and water vapor together. Not a breathable atmosphere, isn't it? Besides, it has freezing surface temperature of minus 60 degrees centigrade. It is because of the rarity of its atmosphere and the distance from the sun. Not a hospitable surface either. We have learnt in this episode how different the pre-planetary and the planetary histories of the Earth have been. Much different from that of Mercury, Venus, and Mars. The ejection event of lunar nebula from the upper levels of the Earth's protomantle was crucial as it accelerated the floating of early crustal blocks. The Earth achieved its core mantle crust structure about 4 billion years ago. But the Earth contains inside its upper mantle a perennial source of molten matter which erupts intermittently even at present as volcanoes. The volcanic activity contributed light density, low viscosity lava, rich in oxyphile and lithophile elements, which formed the crustal blocks. It also contributed the atmophile elements to the primitive atmosphere, which was almost like that of Venus, not breathable. The atmosphere became breathable and benevolent as the earth cooled, initiating precipitation from its atmosphere. We are going to deliberate on how the atmosphere-crust interaction has supported life on Earth in the next episode. Thank you.